So good morning. We're going to do something fun today. I've taught hundreds of classes over the years, and a lot of them are slide after slide, and the information is somewhat interesting, at least to me, because I'm a nerd. But as we're all coming out of COVID, I wanted to do something fun, and so this is not going to be kind of a grind of a lot of technical information. We're going to do a double Jeopardy, and it kind of ties into what we do at Innovatus. So this is a little bit of an infomercial, but not much. So what we're going to do is we're going to ask imaging questions that pertain to the products that we service. Who knows what Innovatus does? Who can best explain it? Gentleman in the corner. Damien. Terrific. Okay, thank you. So real brief history on Innovatus. So we have 3 facilities in the country. We have our MRI Center of Excellence in Pittsburgh, Pennsylvania. How many have ever heard of MedRad imaging coils? We used to manufacture the MedRad line of MRI coils. And we got out of the manufacturing business, but all those coils that we manufactured, those customers came back and said, well, you guys made this, can you fix it? We're like, yeah, let's get into coil repair. So we did. And so we do coil repair in Pittsburgh, and all that repair is done with our manufacturing heritage. And we have a facility in Denver. Denver is our FDA registered ultrasound design and manufacturing facility. In Denver, we make ultrasound arrays for repair. We also manufacture complete medical devices for several of the OEMs. So we make a finished class 2 510K cleared ultrasound transducers for multiple manufacturers. And then in Tulsa, Oklahoma, we have our ultrasound repair center of excellence, where we do thousands of transducer repairs every year. Actually, I was about to tell you how many we've done throughout our history, but I'm not going to, because that's one of the questions. So we're going to dive in, and it's just going to be fun. It's just going to be loose. You guys can, some of these questions, I'd be shocked if you knew the answer off the top of your head, and if you do, you win. Because some of these questions are a little obscure. You can use your cell phones and or laptops if you want to Google something or whatever search engine you use. Yeah, the first one to raise hand gets answered. Now, I've never done this before. This is a brand new format. I was just kind of brainstorming with my marketing guy. And so the way we're going to do it, what we don't want is somebody raising their hand on every single one and not having a penalty. So like in Jeopardy, you lose money if you get a question incorrectly. So if you have a card and you raise your hand and you give an incorrect answer, you actually lose a card. So there's some ground rules in here. Now my clicker died. Hold on. Turn it off, turn it back on again. No, let's see here. Laser works. Why doesn't my advance not work? It was working earlier. Yep. Well, the laser works, and when I first plugged it in, everything worked. Do we have bad batteries? Nope. Our first technical problem. You know what? I can. Are we locked up? Should we escape out and let's start again? There we go. Most of you don't know me, and I've only introduced myself to a couple people in the room so far. We had dinner with a couple folks last night, but my background is service. I did 25 years of field service on ultrasound machines, and I can tell you that half the problems of the world can be solved with turning it off and turning it back on again. So that's what we did. We fixed it. So we're going to learn aspects of imaging device troubleshooting, service, and maintenance. We're going to talk about questions relative to ultrasound, MRI, and quality and regulatory. We're going to get into a little bit of quality and regulatory, not too much. Fun and fast-paced. Only hospital and service personnel. So we don't have any vendors in here, so cool. So the topic will be on the left side of the screen. The question or answer will be displayed. And then you have to furnish the other part. So if I provide the answer, you have to give me the question. If I give you the question, you have to give me the answer. When you think you know the answer, raise your hand, but you better be sure, because if you get one, we have I'm sorry, I didn't even introduce my counterpart here. Cam Conklin. Cam is our Vice President of Business Development. Good morning. That's okay. We're just getting started. You haven't missed anything yet, other than my boring introduction. So a correct answer gets an Amazon gift card. We have a stack of Amazon $10 cards back there. An incorrect answer, if you already have a card, is we pull one back, or you might owe Cam 10 bucks. We'll just go with we pull a card. And the final question is you can risk or reward up to 2 cards for the double Jeopardy question at the end. So let's get started. Assuming ideal care and handling and omitting options for probe repair, what is the expected lifespan of an ultrasound probe? Expected. What's your name? Ian. 7 years. Okay, very good. So omitting options for probe repair and assuming ideal care and handling, 5 to 7 years. We do care and handling training. That's actually one of the reasons why I'm here in Texas. I was doing a care and handling process analysis at a major health center here in town because they were going through lots of TE probes, and I had to go through and try and figure out why. We do a lot of work with them, and our probes are fine when they arrive, but after a short period of time, they start dying, and that's due to improper care and handling. So ideal care and handling seldom occur. That's the good news for people in the probe repair business. And I can train people all day long, and then there's staff turnover, and people forget what we teach them. And so probes start getting damaged again. Our data shows that probes typically fail between 2 to 3 years, and TE probes between 1 and 2 years. That's a little high. TE probes typically fail a lot more than that. And here's a little secret about the probe industry. Probes rarely die of natural causes. Something happened. And if they do die of natural causes, it's usually the wires go. And so 2 items that can greatly shorten probe life cycle are using an unapproved chemical or using an approved chemical improperly. People, when they get a Philips machine, a GE machine, Toshiba, whatever the flavor is, there's always a user manual. It tells you what chemicals you can use on a transducer. You have to follow that because if you don't, you will damage that transducer. We fix all makes and models. I shouldn't say all, but a wide variety of makes and models. And we do accelerated chemical testing on all our materials, on the lens material, on our adhesives, on our plastics. So if the OEM says you can use these 30 chemicals, we take a sample of that material and we submerge it in that chemical for a period of 30 days or longer. And then we test that material for degradation, discoloration, distortion, to ensure that our materials will withstand what the OEM recommends for that particular probe. And there is no universal chemical. I'd love to say that you can use isopropyl alcohol on everything. Don't use it on anything. But you can't. All the different OEMs, they have all these different chemicals that they've validated. We revalidate them on our materials, and you need to ensure that your departments are using the approved chemicals. What is the function or purpose of an MRI coil? What does an MRI coil do? This is a $10 question, guys. Somebody's got an answer. Yes, sir. You mentioned hydrogen. Okay. Now you're getting into the weeds. Yeah. So what an MRI coil does, it's an antenna. if you think about a coil, obviously it's a lot more sophisticated than that, but an MRI coil is an antenna. This is, you can see up here, this is the guts of a coil. As I mentioned, we used to manufacture coils, and now we do coil repair. And so these things are just big antennas to receive the RF signals. When you go into an MRI room and you hear that, those are the gradient amplifiers putting out RF energy, and that coil captures that energy and creates the image that you see. So no coil, no image. Coils come in various shapes and sizes. New and replacement coils, 35 grand to 150 grand. These things are extraordinarily expensive. What's amazing is how inexpensive it is to repair these. When people have a coil go down, MRI is absolutely mission critical to a hospital for patient care and, oh, by the way, for revenue. And so when you have somebody screaming that their MRI machine is down or it's limited because they have a coil that's down, they're not caring for patients, but they're not generating a ton of cash, because that's what those machines do. And so the replacement cost, if you had to go out and buy a new one, 35 to 150. Our average repair cost on a coil is 3 grand, 2 to 3 grand, somewhere in there, which is basically nothing. It's like paying for an oil change on your car and getting your car fixed. So coil repair is very inexpensive. We can turn and burn coils. If it's electrical, we can turn and burn them in a day or two. If it's mechanical, we have a full-on body shop where we can go in, like with these rigid body coils, you know, we'll sand them down and we'll paint putty and then put a clear coat on it, and it looks brand new, and it even smells brand new coming back out the door. So we do have full repair capabilities on over 1,000 different coil models. A written submission, there's a question, a written submission that demonstrates that a device to be marketed is as safe and effective. What is a written submission that demonstrates that a device is safe and effective? You guys can use your phones if you want. Ian? 510K. Yeah, no kidding. He'll be shopping before this class. He's probably shopping online now. So a 510K is a submission that a medical device manufacturer has to submit to the FDA, and it has something called design controls. And within design controls are, did I make the right product, and did I make the correct product, and did I make the product correctly? And there's all these loopbacks to ensure that the user input, the design intent is all followed, and the end result is what you meant to do, and that it is safe and effective. We regularly submit 510Ks because we do manufacture transducer arrays and complete transducers. And some of the transducers we make, we have an NDA with some of the OEMs we cannot talk about, but 2 of them that are on the FDA website, so it is public, we can talk about. We actually make the laparoscopic probe for the Da Vinci robot, and so that little probe that the Da Vinci robot grabs and maneuvers through the body, we manufacture that. We also make this intracranial probe for Hitachi. Hitachi came to us and asked us to design a probe to scan the human brain, which is kind of cool, kind of scary. But what we do is we made this probe that goes through a borehole in the skull, and the transducer rests on the brain, and we can image the brain with ultrasound to identify where there's masses. So those are just 2 of the probes that we make, but we work with the government on some projects on some really cool. We have a prostate device that we're working on that it's a prostate probe with a laser. And so while we're imaging the prostate, this laser will ablate any cancerous tissue. And we're working on, we have a company that I can't talk about, but this company is coming up with a new way of breast imaging. One of the things that we're trying to tackle today is with dense breast tissue, sometimes it's hard to identify breast cancer with really dense breast tissue. So we're working with a company on developing these arrays to be able to further differentiate breast tissue. So we have to issue a 510K for all these. What is the name of the device used to quantify the acoustic output of a probe? So how do we measure the acoustic output or the power coming out of a transducer? Da-na-na-na. Pardon me? No, not a watt meter. Everybody's furiously Googling. Hydrophone, yes. So a hydrophone or an acoustic power meter. Ultrasound transducers put out mechanical energy. We're pushing a pressure wave into the body. Per FDA guidelines, you can only put so much energy into the human body. And so the manufacturers, when they submit their 510K, GE, Philips, Siemens, Toshiba, Sonosite, whatever, they have to submit a 510K and they tell the FDA, here's my device, here's how much power it's going to put out into the body. We do transducer repair. We also manufacture these arrays for some of these models. And so in order to do this safe and effective, we don't have to do this. We are not regulated on the repair space. On the manufacturing side, we are. We're heavily regulated. On the repair side, I can do whatever I want. Now, that may not be safe and effective for patients. I mean, I could open up transducer repair in my garage tomorrow. I know enough to get away with it, and I could probably make a handsome living doing it, but I wouldn't want anybody scanned with my probes other than maybe a competitor. But to do this properly, when you reverse engineer a probe, you need to do acoustic power testing. You need to ensure that the OEM device that was putting out X amount of energy into the body, that you are not exceeding that with your repair solution. That's how you produce a safe and effective product. If you don't, excessive acoustic output can induce thermal warming, patient burns, and or tissue cavitation. Those are all bad things. Insufficient acoustic power can result in diminished image quality. Several years ago, I was with a company that was using, I wasn't here, I was with another company, and we were using this company for probe repair, and everything was lovely. And I was asked to use a different company, and we'll call them Acme Ultrasound. I don't talk about my competitors. And so I was forced to use a competitor, and I got one of the repairs back. And one of the things I've done in my background is I've done clinical scanning. And so I took an OEM probe and I scanned my thyroid. And then I took this repaired probe from Acme Ultrasound. I use Acme just because of the Coyote and the Roadrunner. And so I put the Acme Ultrasound probe on my thyroid. And with the OEM probe, I saw all the blood flow within my thyroid. With the Acme Ultrasound, I could not see blood flow. Now, if somebody out in the field did not have a way to do A/B comparisons, they would have put the Acme probe on a patient. They said, there's no blood flow here, everything's cool. Well, with cancerous masses, cancer tends to build its own vascular system. And so when you're looking at a mass, one of the things an ultrasonographer will look for is, does that mass, if it's malignant, it will likely have vascularity. Well, if you've desensitized that probe, you're going to miss something. And so by using a hydrophone or acoustic power meter, we're ensuring that we're returning that probe. Or what I say is that, I talked to my boss a couple years ago. I said, hey, we're getting out of the probe repair business. He's like, are you out of your mind? That's what we do. I said, no, we are in the probe restoration business. We bring probes back to OEM form, fit, and function. We just don't get them working again. And this is one of the tools that we use. So an MRI scanner is required. You have to have one to test the functionality of an MRI coil, true or false? Yes, exactly. So we actually, in Pittsburgh, we have these MRI emulators. We have engineers and scientists that build these emulators. And so we can actually dry fire a coil within our lab to ensure that coil is going to perform as it's supposed to. There is nobody on this planet that does coil repair that has the resources to buy a test bed for every single coil they repair. You can't do it. It's cost prohibitive. I mean, I mentioned, you're paying $2 to $3 grand for a coil repair. An MRI system costs $1 million too. And we do over 1,100 different coils. So if we were to have a test bed, we'd have to have 200-300 test beds. And so our return on our investment would be sometime around when my grandchildren's grandchildren are retired. And so in order to get around that, not having test beds, we designed these things. You can see in this photograph, we designed these emulators. So this is one of the emulators. You can see them firing here. So what they're doing is they're firing the individual channels within that coil. So no matter the modality, a what should be used to assess image quality? What do you need to use to assess image quality, no matter the modality? Yes, sir. Phantom. Very good. There are phantoms available for all imaging modalities. The good thing about a phantom is objective. As I mentioned, I did service for 25 years. I've done clinical applications. My phantom is my body. Every time I get in front of a machine, first thing I do is my shirt comes up, put some gel on the probe, I pop the probe. I know my body better than anybody. I know exactly what I look like. In fact, back in, I think it was 89 or 90, the company I worked for, Acoustic at the time, used my liver and kidney in one of their ads because I have a beautiful liver and kidney. I still do even after all these years. It's amazing. No, I was doing this carotid. Yeah. Yeah, I teach clinical applications too. In fact, I talked to a group here. One of the things I teach is this class. It's called Ultrasound Applications for Service Engineers. And I teach people how to use the machine. Now, I will never turn you into sonographers. That's not the intent. But it teaches you how to use the buttons and the knobs and what do all these knobs and dials and buttons do on an ultrasound machine. What is the effect? And I teach you how to scan with them. My wife is a sonographer. She went to school for 4 years, and then she did clinicals for 2 years, and nothing drives her crazier than when she goes in and scans she does high risk OB, and she'll scan people, and they'll say, did you have to go to school for this? Can you teach me how to do this? Like, I went to school for 6 years to do this. I teach people how to scan, and I was scanning a student, and this guy had this piece of plaque within his carotid that was just flapping around. It was just dying to break off. And so we took him to the emergency room, and he got cleaned out. And so I probably saved his life by doing that class because he didn't know it. So, and a lot of these images that you see here, this is actually me. And you can actually see right here, see this little white line, see the brighter white line, and then this finer white line below it. That finer white line there, that's actually plaque. So I got a little bit of plaque. So service engineers should never purely rely on clinical images to assess image quality. The reason for that, this is the exact same person, me. It's the exact same machine, exact same probe, exact same everything, except for presets. I changed the presets on the machine a little bit. There are tremendous amounts of variables in human physiology and system setups. So unless you really know what you're doing, you should be using an ultrasound phantom because phantoms do not change, and always use the same settings. So one of the things I did when I was doing preventative, how many are working on ultrasound today? Cool. And you guys are doing PMs. Are you scanning a phantom? Is it the ATS, the big ballistic gel like Mythbusters? No, is it? Okay. So one of the things I did when I was working on ultrasounds is I set up a QA preset within every machine I worked on. And that way, every time I worked on that machine, I'd pull up the same preset, and it was just called QA. And that way, you know you're using the same imaging parameters every single time you touch that machine for consistency. Answer in the form of a question. So now I want you to ask us in a question. What is 1,540 meters per second? Laser. The speed of ultrasound in the human body, yes. So, and that's a tricky question. One of the reasons why I asked this, I don't expect you guys to remember this, and you will never use this in your day-to-day job. At least I don't think so. But the reason I asked this is with an ultrasound machine, we're firing lines of sound. We're constantly firing lines of sound. If this cell phone, the aperture on the cell phone is a little wider than like a linear probe that I would scan my carotid on, but if this is 128 channels or 128 elements, I'm firing one at a time and I'm sending it out. I'm pulsing it into the body, and then I'm listening for the receive signal back. And once I get that receive signal, I turn that element off, and then I go to the next element, and I do the same thing, and then I go to the next one. And you think 1,540 meters per second is really, really fast, and it is. It's kind of fast. But if you're doing it 128 times and you have to keep up a frame rate of 30 or 40 frames per second, the machine starts slowing down. So the more channels you have on an ultrasound machine, the better. But you reach the law of diminishing returns and you start actually slowing the machine down if you try and scan too many lines at once. So best practice. So when we look at transducers, how do we test to see? We call it, internally, we call it time of flight. And time of flight is, for us as engineers, is a very important thing to test for on ultrasound. When you want to ensure that a device is performing as the OEM intended, you measure OEM devices, and then you measure our devices, and you ensure that you have a match with time of flight and a bunch of other parameters. And so when we manufacture an ultrasound array, we make arrays for about 15 or 20 different really popular models that are being produced today. We make those arrays in Denver. Well, the OEM doesn't give us specs, except for one very unique case where we did get OEM specs. So how do we, actually, I think that's one of the questions. I'll skip over that for a moment. But we use these different devices to test time of flight and functionality. So answering the form of the questions, what is the most frequently failed items on an MRI coil? Who can tell me what fails most frequently on a coil? And I'll give you a hint, it's not the coil. Yes, sir. The cable. Yeah. Cables are either damaged or, you know, you look at this cable here, this is an HDMI cable. And if I start flexing this back and forth, eventually I'm going to start breaking the cables within this main harness. And same thing happens with MRI, is those cables will fail. One of the things that we do at Innovatus is we actually manufacture, well, we have a manufacturing solution for cables where you send us either your cable or your coil, and we can build an entirely new harness. One of the common solutions out there when these things fail, because these cables are really expensive from the OEMs. We've seen prices 10 to 15,000 for cables, which is really expensive for really a bunch of wires, but these are very special wires. And they have to be certain gauges and certain impedance and certain capacitance. And so we reverse engineer the OEM cables, and then we rebuild the harness and we put your connectors back on. So if you send us your cable for a fifth, a sixth, maybe even an eighth of the price of a brand new OEM cable, you're getting a brand new cable back from us that is OEM form, fit, and function for a fraction of the price. And so what we've seen out in the industry, we actually got a cable in a few years ago. Somebody had repaired with a paper clip. Yeah, we see all kinds of stuff. Some of the creative engineering solutions out there are not good, and we have to remember that we're caring for patients, and we also have regulatory agencies that are keeping a close eye on third parties these days, and those kinds of solutions are unacceptable. And so what we do is we just make a brand new harness and we put your connector back on, and now you basically have a brand new cable. Did you know? So a common approach is splicing a single wire. So one of the things that we do see is, if going back to my HDMI cable, I don't know how many wires in here. I'm gonna guess maybe a dozen or so. You know, we have video, we have audio. There's, you know, power and ground and so on. So I'm gonna guess we'll call it 10 for nice round numbers. So there's 10 wires in here. If this cable starts failing, do I want to just fix one of the wires that are broken? Well, the answer is no, because if it's like putting 4 brand new tires on your car and one goes bald. Well, I guess the other 3 are pretty darn close to going bald. So you're not going to replace one tire, you're going to replace all 4. Same with a cable harness. You're not going to fix one wire, or you shouldn't, because if you fix one wire, well, its neighbors next to it are on their way out. There's not much life left. And so you want to replace the entire cable. What we've seen is people do splice. You can see up here, this is one of the cables that we've gotten in, and you can see all these little splices. Well, you know, with splices, it's a temporary fix. It's like putting a patch on your tire. It's not a permanent solution. And with these wires, unless you do that splice very carefully, you silver solder it, you may prevent noise. But you know, as I mentioned earlier, these MRI coils, they're big giant antennas, and they're very, very sensitive. And if you start splicing and dicing, you're going to induce noise into your images. So the proper way to do this is not to splice, and certainly not to use paper clips or super glue, but to put a new harness on. And you can go to the OEM and you can get a new harness. But if you come to us, you're going to get virtually the same harness for a fraction of the cost. So what is the main difference when we talk about ISO certification? I don't know, how many of you are on LinkedIn? You see all these companies are starting to announce, you know, we're ISO certified. Can anybody tell me what is the main difference? And this is a question. What's the main difference between ISO 9001 and ISO 13485? Oh. Yeah. So we are 13485 2016 across all 3 facilities, as well as FDA registered in Denver. 1345, one of the biggest differences, and I'm going to elaborate a little bit on your question or your answer, Caleb, is 1345 is specific to medical devices. And what 1345 adds to 9001 is the element of risk management. We want to look, when we're looking at a quality system, you want to ensure that risk management is part of that quality system. We are caring for patients. First and foremost, we want those patients to be well cared for. Second of all, we want to avoid litigation, either as a repair provider or as a healthcare provider. Litigation is everywhere today. So we want to look at, when we come up with a repair solution in Tulsa, it is engineered in Denver first. And so Tulsa will say, hey, we're getting a lot of these probes in. There's a certain solution that we don't have. That goes to Denver. Our FDA registered engineers, they go to work. They engineer a solution. They do all this V&V, and they determine that this repair is safe and effective, and it conforms to OEM form, fit, and function. And then that solution goes back to Tulsa. And then we do risk management. Well, what is the risk if we change adhesives? If we just, you know, you do something as innocuous as, well, we're putting this nose piece on this probe with this adhesive, we're going to move to this adhesive. Where is the risk? Well, there's lots of risk, because if that adhesive is not compliant with the OEM recommended disinfectants or cleaners, and that adhesive breaks down, that probe can come apart. Now we have a problem. And so we do risk management on everything that we do. It's, you know, you can say risk management or you can say CYA, and most of you, if not all of you, know what CYA means. So we do risk management on everything, and that is part of 1345. And so this is just a little matrix. We talk about 21 CFR 820, which is FDA registration, 1345, and a 9001. So you look, 1345 and FDA registration, not much difference. But you get down to 9001, it doesn't do a lot of these different things. What details can be determined based on a probe's model number? So this L12-3, that is a Phillips probe. When you look at L12-3, what can you tell me about that probe? Yes. A linear 12 millimeter. You're half right. I'll give it to you. What's your name? Adrian. Yeah, you're half right. Because where you're going with that is the older Phillips probes, the size of the aperture used to be in the designation. Phillips used to have a probe that it was an L12-5, 38 millimeter or 50 millimeter. So they did put the size of the aperture or the footprint within the probe designation. This L12-3, what it tells you is it is a linear. And so we have this type of image formation. The 12-3 gives you the frequency range of this transducer. And so this transducer can go from 12 megahertz to 3 megahertz. And so if we look at all these different probes, these probes here, this is a Philips probe, this is a GE probe, this is a Siemens probe. The C means curved, it has a curved array. And if you think about a linear array, if you just took this array, and we actually do this, if you took this array and you bent it, it becomes a curved array. And the advantage is look at this wonderful far field we get, because all these lines fire perpendicular to the face of the probe. And so that's how a curved array is made. It's not made curved. You have to make it curved. And so in Denver, when we make a curved array, we have a dicing saw and we slice silicon to make transducer arrays. And these things are paper thin, and the elements are the width of a human hair. I mean, we're talking micro surgery here. And then when we get done with all that, and we're like, oh, thank God it worked. And then you have to take a mold. And this mold for some of the probes is about the circumference of this, whatever this bottle is, Omnipake. I'm not drinking that. But what they do is under this array is there's these Kevlar strings, and you have to pull the array over this mold to form that curve. And about 30% of the time, the array snaps when you do that. And it's like, oh, God, I got this far. It's like you're in bomb disposal, and they're like, oh, God, please don't break. But the OEMs do the same thing. That's how the OEMs make theirs. And so we make ours the way the OEMs make theirs, and their yield rates are probably the same, if not less than ours. And so if it breaks, then you have to throw it in the trash can, and you have to start all over again. And so these particular probes here, so these are convex. The IC means inner cavity. That IC 5-9, that means inner cavity. That means it's either an endovaginal or an endorectal probe. And then over here, the S stands for sector or vector, where we have that V or that pie-shaped image. So additional information, this particular probe is a matrix probe. So traditional probes have just rows of elements. A matrix probe has rows and columns. And the Philips X matrix probes, how many deal with Philips X matrix probes in here? X5s, X7s, X8s? Yeah, they have thousands of elements. Oop. We can repair the X matrix probes. We cannot repair the array itself. Nobody can. Philips can't. I've heard third-party claims of, yeah, we can repair that array. No, you can't. Nobody can. It is, I shouldn't say impossible. I guess if you spent years of millions and millions of dollars, you might be able to figure out how to do it. But why not just buy another one? But we have full repair capabilities on everything up to excluding the array. So we can fix the connector, we can fix the cable. We manufacture a bunch of different cables, and I think that's one of the questions as well. So we can restore the safe and effective performance on the Philips X's, even if fluid invaded. One of the most common problems with Philips TE probes is they get breaches in the insertion tubes or the bending rubber, and you get fluid in, and then the probes blow up. We can even fix those. So although MRI technologists perform frequent quality control checks on MRI coils, should coils be included in a comprehensive PM program? Do we want to do PMs on coils? You got a 50-50 shot. No PMs on coils? We actually want to. They're very analog. They can drift. You had a 50-50 shot. They can drift out over time. And the performance will deteriorate. Actually, since these are analog, they are not digital in nature. At least, some of them are hybrid, some of them are digital and analog. You can get those problems. So for in-house, you want to do a thorough visual inspection, and we can do a one-day turnaround. If most people do not do preventive maintenance on their coils. Nobody wants. I mean, you try and pull a coil out of an MRI technologist's hands, you're gonna go to the floor. They're going to take you down. They're not going to give you that coil. But you can do these preventative maintenances in-house. Okay, next question. An ISO quality standard for assuring biocompatibility. What is the ISO standard for ensuring biocompatibility? Ian. 10993. Man, quick. Um, can you follow up and tell me why that's important? Yeah, any medical device that has patient contact should be, and we're not required to do this, we do it, should be 10993 compliant. 10993 is not a certification that you can hang on your wall. We hang our 1345s on our wall. We're very proud of it. But 10993 is not a certification that you receive. It is a certification that you are compliant with. And so with our materials, whether it's our lens material on a probe, whether it's our cable jackets, our plastics, our adhesives, we ensure through an outsourced company that our materials are biocompatible. So we send our materials off to this company and they do their testing and they come back and they say, yes, your materials are safe and effective for mammalian tissue. And then we can implement those materials into our processes. This is one of those extra steps that we go through that we don't have to, but we do. So OEMs do this. So the OEMs have to do that. And that's that whole, what we're talking about now with MITA and the right to repair and all that. The OEMs are saying, well, those guys, you guys don't have to play by the same rules we do. The third-party service providers, and you guys are third-party service providers. We are a third-party service provider. We don't have to play by their rules, and they're right, but we actually do. We choose to play by their rules. So we are not required to use ISO 10993 parts. One of the things that this particular probe here, when I was talking about adhesives and chemicals and all that, that particular probe here, that's a GE RIC 5-9-D. About a year ago, we got in a rash of those. We were getting in dozens and dozens every week. There was another third-party provider that was using an adhesive that was not tested for a disinfectant device called Trophon. And this Trophon device was breaking down their adhesives, and these probes were coming apart inside patients, which is a very bad thing. And so because of all the testing that we do, our materials are compliant with Trophon. So all those probes, and we actually got some from an OEM as well. But since we do testing, and we actually worked with the manufacturer of Trophon, which is a company called Nanosonics, and they gave us their seal of approval. They said, yeah, you guys have tested all your materials with our device, and they will withstand the abuse that we put on them. So what could be the result of incorrect transducer lens dimensions? So if somebody were to do the shape, thickness, or incorrect materials on a lens, what could be the downfall of that? I mean, we think about a transducer lens, it's just a simple barrier between the probe and the patient, right? Nope. If somebody does a lens wrong, like if somebody were to take my glasses and give me glasses with a different prescription lens, what's the effect? Pardon me? Cause damage, possibly? Yeah. It can cause damage. If you put the lens of a transducer on too thin, that transducer will put out more power than the OEM intended it to. And again, when you do repair, you have to go back to OEM design and intent. You cannot improve the OEM design unless you're filing your own 510K. If the OEM did it this way, we are, I should say we're required, but we're not, because we're not regulated, but we should do it exactly the way the OEM did it. If you put on a too thin lens, you're putting out too much power. If you put on too thick of a lens, you're not putting out enough power. You're going back to that scenario where I told you where I was scanning my thyroid and I wasn't seeing any blood flow. I had perfectly fine blood flow. It's just that Acme Ultrasound put on a really thick lens and it was killing the acoustic intensity going into my body. And so I wasn't picking up all that sensitive blood flow. It can, yes. Too thin a lens, you're putting out too much power. Too thick a lens, you can miss things. And if the shape is wrong, I actually heard from, and it was actually from Acme Ultrasound, one of their engineers. I said, tell me about your lens process. And he said, well, the lens doesn't really do much. It's just a barrier between the probe and between the array and the body. So we don't really pay much attention to it. And I'm like, you're fired. You will never touch one of my probes again. The lens is not a barrier. The lens does all kinds of different things. And the reason it's called a lens is because it is a lens. It's an acoustic lens. I mean, these here are optical lenses. The lens on a transducer is an acoustic lens, so it focuses the acoustic energy. If you don't have the proper shape, you're not going to focus the beam properly, and you're going to have poor image quality. Poor image quality, poor focus, incorrect measurements. You're looking at these images here. By the way, this is my thyroid. So this area right here and this area right here. So OEMs spend considerable efforts choosing the correct material, shape, and dimension of the acoustic lens. So we have to do material analysis, chemical, again, biocompatibility, precision molding. 10. And then power testing. When we create a lens, we do power testing. Are we still putting out the same amount of power, no more, no less, than the OEM intended? And then we do image testing. So what is the single component within an ultrasound probe that, if damaged, greatly affects the probe's repairability? The most fragile, in the corner. Who was first? Yes, it is the array. So what you see here, these individual elements, again, we make these in Denver. These crystals are the width of a human hair. The space in between the crystals that we have to cut when we dice these ceramic materials, they're 1/5 the width of a human hair. Now imagine a saw blade that I'm a tool guy. I have tons of tools at home. I have a table saw, and I have circular saws, and I have hand saws. I mean, you think about how thick those saw blades are, right? Imagine a saw blade that is 1/5 the width of a human hair. It's like tinfoil. It's made out of aluminum and it has a diamond edge, but it's like tinfoil. And we have to spin it up to about 40 or 50,000 RPMs to get it rigid. And then we have to slide the ceramic through it 127 times, and then we have to water cool it at the same time. It's crazy science. It's really cool. In fact, there's a video that shows us doing it. There's an 8-minute video on our website. If you guys don't mind, I'll follow up with you with an email, and I'll send you a link to the video if you want to see how probes are manufactured and repaired. You can actually see this dicing saw at work. It's like Star Trek stuff. So damage can result in dropout. So we manufacture arrays, as I mentioned. I'm going to kind of speed up a little bit because we're running low on time. I don't want to go over. So repair solutions, you can get replacement arrays from a qualified supplier, which we are the only transducer repair company in the United States that has our own internal manufacturing of arrays. We're the only ones that do it. And we're the only ones that are FDA registered for it, other than the OEMs. We can surgically repair the array. We actually have technology where we can lift these hair width elements from donor probes, and we can transplant them onto probes that we're repairing. So if we don't have an array solution, we can actually fix an array. And we manufacture the equipment that do it. You can't buy this equipment anywhere because we make it, and we only make it for us. So flex coil should never be picked up, moved, or transported by the what? How do we never, ever want to move a flex coil or transport a flex coil or grab a flex coil, I guess? Nope, not cable. By the phone, yeah. These look like handles, don't they? It looks like a great place to grab it. No, that is high density foam, and inside there are loops, there are antennas. And if you grab it by that handle, or what people think is a handle, you are going to break that coil. And then we have to fix it. Or you have to buy another one from the OEM. So that is a no-no. So you can see, we show a coil here that has started to break apart because people have been using that as a handle. It looks like a handle. They should put do not grab here, kind of like airplanes, no step. You know, you see on aircraft, no step. It should be no grab. But we don't do that, and the OEMs don't do it. So did you know common approaches to damage and foaming are patching and splicing. We've seen coils come in, these flex coils where people super glue, they use silicone. Again, these are medical devices. You need to do this right, and the repairs aren't all that expensive. When you consider the cost of the device, I mean, if you pay $2,000 to $3,000 for a coil repair, that revenue is generated on the next patient, not the next day or the next week or the next month or the next year. It's generated on the next patient, and then you're done. So we highly recommend you do that correctly. So what is the typical length of a cable of an ultrasound probe? Kind of a trick question. You were in my class, man. I'm gonna laser you. Typical length. Throw me a number. 3 feet? No. That's a good answer, but be more specific. Huh? Yeah, 7 foot is about average. It's 6 to 8 feet. We have a winner. It's 6 to 8 feet, and it varies. With a standard abdominal probe or a vascular probe, you're probably looking at 6 feet. When we get into cardiac probes, it goes up to 8 feet just because of the route the cable has to take and for the echosonographer to do the exam. For endovaginal probes and endorectal probes, it's usually 9 to 10 feet just because it is a more circuitous route for, for patient comfort and for the exam ergonomics. And so the average is 6 to 8 feet. So it is model dependent. These are all the different wire properties. One of the things that we do in Tulsa is we manufacture over 80 different transducer cables. There's on the market, there's a one-size-fits-all cable where you can buy raw cable, slice and dice to the length that you want, and put it on, and it'll fit any transducer out there. We don't believe in that because they have all these different properties. We have capacitance, inductance, resistance. Is it solid or stranded? What kind of insulator? Again, OEM form, fit, function. If the OEM did it this way, a repair provider should be doing it this way. So cable repair, people harvest old cables. We don't do that. They cut back. They'll splice individual wires. We don't believe in that either. We'll just make a new cable. How many flexes do you believe this cable withstood before beginning to deteriorate? So this is a torture test that we do in Denver to test our cables to make sure they're as robust, if not more, than the OEM. Ballpark. How many twists and turns do you think that poor cable withstood before it started screaming uncle? 150? 1,000? Oh God, if it's 1,000, we're out of business. You're much closer. This cable withstood over 100,000 flexes, and we're doing, you can see we're doing 180 this way, but we're doing 360 this way. So we are torquing the living tar out of that cable to see how long that cable will last. And so that's our way of testing for accelerated use. So well over 100,000. We have a winner over here. So we flex that cable 180 and 360. That particular cable, yeah, that particular cable screamed uncle at 101,871 cycles. What is the typical wire gauge in a transducer cable? Typical wire gauge. You think about my hot water at home, 10 gauge wire. My electrical outlets are 12. My lighting is 14. So if you use that as kind of a guide. 44, very good. Yeah, 42 to 44. These wires have to always be soldered by hand. When we put a new cable on a probe, so you think about coaxial cables, we have the insulation, we have the shielding, and then we have the center conductor. The center conductor is smaller than the width of a human hair. And so we have to solder the shield, and we have to solder the conductor. And we have to do that 128 times on the probe end. And then we have to do it 128 times on the connector end. And it's all done by hand. Are third parties required to repair medical devices to meet OEM specifications? Are we required to repair to OEM spec? No. What's that? Well, we don't have, there's a trick question. We don't have OEM specifications. The OEMs don't say, hey, yeah. The OEMs don't say, hey, Innovatus, you're gonna compete against us and repair our probes. Here's our specs. Here's our directions. Go ahead and follow these. We can't do that. And so we have to develop our own specs. And that's why we have an acoustic lab and all these engineers. They reverse engineer the OEM devices. We figure out OEM intent, OEM form, fit, function. Now we have our own specs and we repair and design to those specs. So best practices, I'm going to move along really quickly. So double Jeopardy, final question. 2 cards. And how many ultrasound probes and MRI coils has Innovatus repaired throughout our lineage or history? It's on the website. Innovatusimaging.com. Gotta raise your hand, somebody. Terry. 35,000 what? And how many probes? And he's gonna find it. It's 160,000. So we've repaired over 160,000 probes to date, 35,000 coils. We're probably gonna do 4,000 or 5,000 probes just this year alone. So we have a lot of probes coming and going. And when we do a repair, we do offer the longest warranty in the business. Our warranties are longer than the OEMs on new devices. So if you buy a TE from the OEM, it's going to be a 90-day warranty. We do a repair on yours or we swap it out, we're going to give you 6 months. They offer 90 days on a standard probe. We give you a year. So that's the first edition of Imaging Jeopardy. Thank you so much for coming. Does anybody have any questions at all about imaging or ultrasound, MRI? Yeah, the QR code, scan that. No questions?